Okay, we have 1 more minute to go. By the way, midterm is just an exam, a paper test. You're not allowed to take in any electronic devices. This is the page 1. You can see this is an open book test. There will be 3 questions, 8 pages, and so on. You are not allowed with any electronic devices. Okay, the use of mobile phone, laptop, and calculator is not allowed during the test. On the other hand, practical exam, which is in the last week of May, this is the one that you have to bring your own laptop, charger, and extension cord. Okay, 7 o'clock, let's get started. Today is the review for lecture 9, searching and sorting. All right, we are working with, so this particular lecture, it demonstrates how to use list as a data type or data structure for applications. So in particular, we use the list because we want to do sorting, and in doing sorting, we do a lot of updating or switching or moving items around a lot. So it's no point in using tuple, but we want to use list here as an example. All right, and we are dealing with big data. I mentioned this before. All right, in dealing with big data, we are 5 types of things that we do. All right, searching, sorting, filtering, mapping, and accumulating. All right, searching and sorting are what you see in lecture 9. Filtering is a way that you go through all your records and take away those that you don't want. Right, and mapping is going through all your records and trying to do some computation to each record. Accumulating, it's also going through some records, and at the same time, you are trying to aggregate to get some statistics about all the records that you have gone through. All right, so these are the 5 types of things that you have to do with for big data. This big data, I guess your generation is so familiar with it. In Google search, whenever you search something, you are actually getting a bunch of things, and a bunch of things are in the collections of lists. And there is an array in a traditional programming language. In here, we talk about it as a list. All right, because all the kind of processing you're dealing with cannot run away from all these 5 types of things. That's why we have also what we call the signal processing way of getting things done. Basically, going through stages of conversion. Any one of these could be a searching. Another one of these could be a filtering, as what you saw here. And another one could be mapping to try to do some calculation according to it. And so this thing can chain up so that you can have the different purposes already built into each stage, and you can chain it up to serve a particular purpose of getting the final result. All right, so lots of this kind of function can be chained together. No matter how that I can set my exam questions, in actual fact, they cannot run away from all this. So all the questions that you're going to see in all our assessments are some form of manipulation dealing with all these things. So nothing particularly difficult in a way, but there could be quite a bit of steps that you have to deal with. All right, so that it's lecture 8 and lecture 9. And for today, sorting. Sorting it's during my generations, actually, sorting there's quite a bit to study. In fact, what you are now dealing with is only one lecture. So in one lecture, we can't do much for you. But at least you can see that there are already variants or various flavor of things. All right. So like what I can show you here, it's this one. So here are the various sorting algorithms. It's not the exhaustive list here. In fact, there are many more. All right. So then each one has its different kind of time and space complexity. When it's in place means that you don't use extra space. But you see that this guy already completed. This is a random set of input. This guy already completed the calculation or the sorting, while these two guys are still doing their job. In fact, these three guys are of time complexity n squared. Therefore, they are kind of slow when dealing with random input sets. On the other hand, these few guys are in general O of n log n. That's why they could be done very quickly. Right, you see. And these are, and in studying sorting, we also take into account that there are various kinds of input. In this case, this is a random case. This is nearly sorted. And because different characteristics of all these kind of input, all the algorithm behave differently. In fact, in practical situation, you could see that at some point it started out with maybe a heap sort, and at when things are almost sorted, you may switch to insertion sort because they are all in a different kind of advantage in dealing with different kind of types of data. All right, so this is a nearly sorted case. This is the see nearly sorted case. This guy very fast insertion. All right, while this n square thing is still taking its time. All right. On the other hand, the reverse one, insertion is quite bad, as we can see, and all these guys n log n are actually quite good. All right. So different kind of inputs, the behavior are quite different. Okay. So in sorting during our time, we spend about one semester because there are so many types of sorting algorithms, and there are various ways that you study to understand the time and space complexity, and then you learn about the tricks in analyzing the algorithms. All right. At this point, I should say that until today, you are already gone through these few stages. Yeah, you started out with playing with the code, right? You in the either you just type something, you can show your pictures, picture language, and then we talk about how to write good codes, respecting the objective and the assumption, and then we study time and space complexity to get efficient code. And last but not the least, actually, there is something which real computer science students should know. It's that you have to learn about proving correctness of the whatever you write. So, some of this code that it looks innocent, but you cannot tell. You have to argue how things are like. For example, this code, this is selection sort. How do you know that this guy is actually doing the job of sorting it out for you? All right. So this is about the proof that we needed to do. So we needed to prove the correctness of the whatever you write. Usually the problem comes from the looping. Okay. Any statements are quite simple, but because of looping, things changes, and the things that changes, it's dynamic, and then therefore you have to argue about these dynamic changes and what happened as a result. Okay, for today, I want to show you some of this proof. At least this will differentiate you from those people who know only just how to write codes. Okay, by writing code is not enough because you have to convince other code is written for other people to understand, the other people to read. So you have to make sure that the guy who reads it believe you that whatever you have done is a correct thing. Okay, so let's go through a few proof. I'm going through the selection sort, merge sort, coin change, and recitation number 4 last week, and some of the thing that we wrote. All right, so let's take a look at selections. This is a selection sort. All right, this is a set of numbers. Selection sort is going through the numbers and pick out the one that's smallest and move to the front. All right, so currently 15 is the smallest. Now become 9. So 9 is moved to the front. Next, 15 is the smallest, and so 15 stay. Next, 29, 22 become the smallest. and now 15, and it moved to the front, and so on. Okay, so this is selection sort. This is in place selection sort. In place in the sense that it actually doesn't use extra space. It just within itself, it interchange the number. But as you study my lecture, you will see that this in place sort, it's actually not stable. All right, meaning that the 15 that was together in this manner, originally in the other manner, may not be in the same order. All right, I'll leave that to you to study. Okay, here is a copy, a version of the uh, selection sort. Okay, and I actually put up another version for you to try in the forum. Last night I put it up. You can try this. This is an in-place selection sort. This is the one that actually shown in the video, in the animation. Okay, so let me do this one for you. All right, so how does this code work? This is a selection sort, and this is the input list. It has to be a list. It cannot be a tuple because you want to change things. Of course, if it is a tuple, you would have to copy into a list also. All right, so you call it, and then now here. So the first statement is you make a list, a list. The input is a B list, so you make a copy to here. By making a copy so that we don't destroy the original B list. You know the side effect that we talk about when you pass things into the routine. Usually you do not want the routine to change whatever it is in there, unless this is a function that which its purpose is meant for changing it. Otherwise, we always want to maintain it because you see that you are actually returning the sorted list. So this is the program you copy, and then the sorted one that you wanted to return originally initialized to empty, while the A list, means the copy of the B, is non-empty. All right, you do these steps until this guy is empty, you return this sorted list. So, and this loop is to find the smallest guy in the list. So smallest is initialized to this. Is an assumption that we don't have number larger than this. Then for every element inside the A list, if you find that that element is smaller than the smallest, then you change the smallest to that element. And then the next two statement is simply at the end of this for loop, you just remove it from the A list and put it into the sorted list. All right, so this is the program we want to prove. So when we say that we want to prove its correctness, we for sure wanted to argue that sort A is the giving us the B list in a sorted manner. All right, so that is quite obvious. Okay, another less obvious thing is that you must also state that sort A contains everything in B list. Okay, if sort A is sorted, that is not good enough. Sort A has to have the same elements as those in B. All right, so for sorting, we mean to do this. Okay, so there are two conditions that you have to do. All right, so when you see a program, you have to start it out with what are you trying to argue that this program has achieved. You have to, in this case, we have two conditions to achieve. Number one, the sorted A has the same set of elements in the input list B list. Right, it has to be the same as B list. Right, that is the minimum, right? You don't want to sort and then you lose some guys. Okay. And number two, elements in A is indeed in the sorted order, right? So that is how it's being sorted, right? But other than these two conditions, actually, there is one thing still missing to prove the correctness. The missing thing, which is what we don't have to worry for now, it's that because we know the time complexity of this guy, it's O of n squared. And once you know that it's O of n squared, you know that the algorithm actually terminates. Okay, so the program has to stop. If the program doesn't stop, then it's no point that you meet these two conditions because sort A can never get returned. Okay, so it has to stop. But by knowing that the time complexity of this code is O of n squared, you indeed know that it is terminating for sure. Okay, and that is to say that A list for sure at some point A list is empty. Therefore, you can reach this statement. All right, so this is not a big argue here, but that should be enough for us to talk about condition 1 and 2. Okay, so how do I do this condition 1 and 2? You have to be going through the step by step. So here should be, let me do condition 1 first. So we have this guy. So we have to think of a way to argue that at the end, sort A is actually the same as B list. All right, so how do we argue that? So here it's the trick. Right, the trick is that you define this thing. Sort A union A list is equal to B list. All right, so this is the trick. Right, you started out with sort A is empty, so this is empty set union A list. And A list is actually B list, right? Because it's the same copy. Therefore, this thing is true before you enter into the while loop. As I told you just now, when you enter into the while loop, things can change. All right. So before you enter into the while loop, you argue that you already have this. And you want to maintain going through the while loop, you still have this. This is so-called the invariance, meaning that without the S, meaning that this is always true. Okay, so this is we started off with sort A union A list to be the same as B list before entering, and then after you enter, you want to continue arguing. This is the case still every time you go through the loop. All right, you see that every time you go through a loop, changes happen here. A list got removed, sort A got append. So these are the two statements that are affecting this condition. So we see how to still maintain that condition. Okay, so here is how we maintain that two condition. All right. So this 1.1, 1.2, 1.3, I use this numbering to indicate I'm trying to prove condition 1. So at this moment, whatever we remove from A list, it is added immediately into sort A, right? So we can confirm that sort A union A list is still the same as B list, right? There shouldn't be any doubt, right? After this statement, maybe something is wrong, but these two statements together, you still have this because whatever missing from A list is now added into sort A. Therefore, whatever you started out with, sort A union A list is B list, this is still maintained. All right, so 1.3 is true. Then after that, because at the end of it, so this thing going through all the time and you never got any problem because this is always true. At some point, this A list is gone because it's empty, because it keep removed. And so it become empty. And so 1.4 exiting the while loop, A list is empty, right? So when this is out before you return, it is empty. And then 1.5 says that because A list is empty, so A is equal to B list, right? Because A list is empty. So we do have sort A has the same same set of elements in this as a B list. All right. So this conclude that condition 1 is fulfilled. All right. So all these whatever I put down here are kind of like remarks, but in actual fact, when you study programming languages, you can actually use symbols to represent some of these arguments. All right. So anyhow, all this English should be enough to convince you that whatever we have done here, it's indeed concluded with 1.5. 1.5 means that sort A is the same as B list because A list is empty. All right. Now condition 1 is fulfilled. Next is condition 2. Condition 2 is to say that sort A is arranged in increasing order. All right, so we have to argue about that. And it started off with here, we are going through to get the smallest guy. So you have to believe me that this loop is to find the smallest guy while those among those guys is still inside A list. Okay, so what we have is A list contain all the numbers larger than those in sort A. All right, this is a starting condition because why? A list is the same as B list, but sort A is empty initially. All right, this is initially true as sort A is empty. So you cannot question this. This is true. Then sort A has the numbers already sorted before entering the for loop. This is true also because sort A is initially empty. All right, so before we actually getting this smallest guy, we have know that sort A is nothing in there. It's already sorted. Nothing is also the same as sorted. Okay, and so now we going through this guy. We are getting smallest guy in there. So once we have that, what do we have achieved? We would have done on then we will have done 2.3 at the end of the for loop. Smallest is the number in A list, which is indeed no larger than all those guys in A list. That is to say that smallest is among all the guy still existed inside A list to be the smallest. Since the number in A list are all no smaller than those in sort A, as what we have from 2.2, the smallest we found is still no smaller than all number in sort A, correct? Because sort A has initially has no number. The first time we get the number, which is the smallest, and then therefore it is the smallest, still larger than everyone inside sort A, because sort A initially is empty. All right, so then the consequence of all these statements come together. All right, 2.5. Smallest is now added to sort A. Right, these two statements says that. This addition maintains the order of item in sort A. Right, the first time when sort A is empty, you know that that is true because the new guy I just got appended is no smaller than all those other guys already in sort A. And for the very first time when it is moved and added into sort A, it indeed has the smallest from there. Then from one round to the next round, while loop, we get the next number, which is still larger or equal to those in sort A, but smaller than or equal to all those still in A list, and added into this, right? The summary is then we maintain sort A sorted, and all elements in A list still no smaller than those in sort A. All right, so, and then we conclude with 2.8 once you get out of the loop. All right, you got 2.8. Since A list is now empty, sort A equal to B list, and sort A is sorted, condition 2. And then you take 1.5 and 2.8 together, you have what you wanted, and sort A is actually the sorted values of list B. This is how the argument is formed to make sure that this code is working. You can do the same for the one that I show you here, okay, which is an in-place sort. And that will be a good practice. Next, I want to show you it's a merge sort. Are you okay? Give me a check if you're still okay. Right, this part of the kind of material, it's a little bit advanced, but you may not be needed to craft up statement by statement. But at least you should know how things are like. At least you should know what are these kind of things that you needed to prove. Okay, you needed to ascertain that these are the things that maintain, or these are the things that which happen that you can argue that they are actually ascertain they are true. And then you can have a correct algorithm. All right, next one is it's the merge sort. All right, merge sort is divide and conquer. It's a standard thing. 16 numbers here divided into two halves, and then into two halves, and then recursively doing the half. All right, let's see. Okay, so there are 16 number, 8 of them, 4 of them, 2 of them. The 2 will be sorted, and then these 2 will be sorted. Okay, and then go back. And then these 4, it happen to be sorted, but they still have to go through the motion. So these 4 are sorted. And then these 4 come, these 2, and then they sort. And then these 2, they sort. They are sorted actually. But these 4 are not sorted, so they have to sort by merging the 2. So now they are sorted. And you go back to, and then this 8 has to be sorted. All right, so this is how it works. Now, so here's the code. So merge sort, if the length is less than 2, you just, meaning is 1 or 0, you just return the list. Otherwise, you do the left half, which is from the 0 until half point. Then you do the right half from the half point to 1 plus half point till the end. Okay, and these 2 are assumed to be correct because by induction, merge sort is also merge sort. And then these 2 have to be merged together. So the bulk of the challenge is with the merging. So this is the merging code. All right, so we have to argue that this merging indeed will merge correctly to return something sorted. So that it's the statement that we needed to argue also. So maybe just put out some statement here. Okay, maybe I'll just do this. All right, when there is just 1 or 0 item, then we are done correctly. This is the base case of induction. By inductive assumption, the following 2 are correctly done for the left and for the right. And then the heavy machinery is on the merge. So now again, the same thing, we have to decide on two conditions. What are the 2 conditions with respect to this routine? So this routine is talking about left and the right and is returning the result. So we want the left and the right to be union of them to be inside the result. At the same time, the result is also sorted of elements in of the left and the right. Given the left is sorted, given the right is sorted. So we have these 2 conditions. The result has all the elements in the union of left and right. These results, or there should be an S here. Elements in the results are indeed sorted. All right, so this guy is indeed sorted. Okay. So these are the 2 statements that, having seen this, you should at least know them, even though that you may not know how to do it the way that I'm going to show you in shortly. Okay, so we have this. So we have to do something similar to this guy using the trick that we take this union something and then we equal to whatever input. All right, because ultimately we are going to remove things and append things. So here it's what we have. All right, the left is sorted with smallest in the front. The right is sorted with smallest in the front also. So we want to argue then we set it that result union left union right. It's the same as the input left and input right, meaning that the original input left, input right, these 2 together is the same as result union left, union right. The left is our left here. The right is our right here. The result is initially empty. So because the left and the right, initially this left is equal to the input left, this right is equal to the input right. Therefore, empty set union the input left, of course, this is equality, it's established. Okay, so now the things going to happen is here, because you are going to remove things and from the left and add it to the result. So this has to be ascertained. So the 1.1, now 1.2, append to results follow immediately by removing from the left. All right, or removing, I can move this statement to the, oh, I have to add first because otherwise I make a mistake, all right? Because the left 0 is still there. I need to add first. So maybe I can change this statement a little bit. All right, meaning that the left 0 is removed immediately after added into the result. Okay. All right, so we maintain this same thing. It's just taking one thing out and put it to the result, and therefore the original equality maintained, right? Originally it was true before you enter. Now you enter and then you try to do something. You are taking from one set into another set. So of course, then this it's going to still remains true. Okay, so there's no this problem with that. And if you do it for the right, then it's just a symmetrical case. Okay, so that it's true. So now this thing it's going through again. As you see, the problem comes from the looping, or the challenge come from the looping, not problem, but challenge. And so once this guy is done, so anyway, as long as you are in here, you are safe, all right? Because this is removing one thing from putting into the result. So this is established. So the moment you get out, okay, the moment you get out, what happened? So this is what happened. The moment you get out at this point, we still have the same thing as before. Also, because now if either when you get out means that the left or the right must be empty, or both are empties, right? So if left is not empty, we are going to put everything in the left into the result. If right is not empty, we're going to move everything from the right into the result. If both are empty, we put nothing. Right. So things is going to change because of this again. So we are going to put in our statement. Okay. So 1.3 and then now 1.4. This means that right is empty. This also means that result has all the elements from the right already, right? Because if left is non-empty, then the right must be the one that is empty. So result union left union empty set is the union of input left union input right. All right, that is no change to this statement, just that right is not empty set. Now we put everything in left into result, so result is indeed equal to this. All right, so that is true. It's the same argument for if right is non-empty when you put everything from the right into the result. Okay, so this is how it will be the case. Else if, right, if the right is the one, then a symmetrical case 1.4 is 1.4a, 1.5 is 1.5a. All right, so the last, actually combining these two, we get the result 1.6. So result is indeed in either cases, or in either case, condition 1 is done. Okay, so this is condition 1 is done. We have established that the result indeed is the left and the right. Next, we want to be sure that the results are indeed sorted. Okay, so this is again the same thing. So when you have to argue what left behind versus what is being put into the result. All right, so at this moment, I can quickly just cut and paste for you to see. While left and right, okay, 2.1, at this point, both left and right are not empty. So we can have left 0 and right 0. Then we also know that left 0 is the smallest of all elements in the left. Same for right 0, it's the smallest of all elements in the right. So we just need to take these two guys and compare who is the one that is smaller. If it happens that left is smaller than right, that means that left is actually smaller than everyone in the remaining left and the right. All right, so you simply take the left into the result. Okay, so this is how it is happening. Right, so if left is the one, then you take the left, means that left is the smallest among all the left and the right. And so this is to add the smallest into the result, while this is still larger than all those added into result earlier on. In saying so, we also asserted that result is sorted with a new addition. 2.4, numbers in result are still no larger than those in left and right through each loop. Okay. And a symmetrical case for the case of the right. All right, this is a symmetrical case. Then at the end of it, once you get out of the loop, you are now at 2.5. Results remain sorted in increasing order because every time you're going through the loop, you maintain it. Therefore, it has to be true once you exited from it, right? And now we also know that either left or right is now empty, or both are empty. It's possible also. Okay. Then I just needed the 2.6. All right, result remains sorted because it is extended with those number in left that are sorted, and these numbers are actually larger than those in the results. And then you have this is a symmetrical case. All right, so this is 2.6a is a symmetrical case. Okay, and last you can then conclude with 2.7 after the extension 2.6 and 2.6a result indeed is sorted for all its elements. All right, so there's established condition 2. Okay, so these are how we are done with proof. So this kind of proof is writing out the statement by statement. As I said earlier on, actually some of these could be represented as symbols when you learn about those how to do this kind of proof. Okay, the minimally you should know what are the conditions that we are trying to prove. As to the details, so these are just details. Yes. Okay. You give me a check if you're okay, then I can move on to the next one. All right, this is kind of complex if you are seeing it for the first time, but you can review the video at speed of 1.5 times to better appreciate it, hopefully. I want to show you the next one, which is the coin change. So you know coin change, this is taken from your lecture notes. You want to change this amount with n coins. If the amount you want to change is 0, meaning that there's only one way you can do it, don't use any coin, okay? If the amount is less than zero, there's no way you can do it. You have zero ways of changing it. If the number of coins you have so far is zero, no matter what amount you want, you cannot do anything. It's zero ways. So these are the base cases. Okay. And this is the main one, which is the recursive. And you see that the way to change a amount is to use one particular coin and one or more times, and or you don't use that coin at all, and you maintain that amount. Okay, so this is a plus because this one is talking about those changes with at least this particular coin. This one is talking about those changes without using that particular coin. All right, so the sum of the two, it's not overcounting. This by itself is undercounting. By itself is undercounting, but they are complementing each other. When you add them together, they are actual count. Okay, but we still have to prove this. So how do we prove this? All right, here is the proof by induction. So let me just cut and paste and quickly show you. All right, this is a proof of correctness. The base cases I show you, these are the base cases. They are all correct. Then we want to argue that why this statement is true. So this statement is true, have to be the case that we want to count something, and then why these are the formulas that we are talking about. All right, so these are indeed the case because in words, it means that the number of ways to change amount A with n coins, how do you do it? Is to do it in two different ways. One way is don't use a particular coin. That particular coin, I don't use it at all. Another way is to use that coin one or more times. Okay, so these are now become two sets. One is called set A, the other one is called set B, and they are mutually exclusive. They do not overlap each other. So by adding the two together, you are not overcounting, okay, because there is no overlapping. Number two, they are actually uh, the two complete counting because you either use that coin or you don't use that coin. Okay, so these are indeed the two numbers we need to find and add them together. So by right, and then as such, and these two numbers happen to be what we have in the formula. All right, A is actually this, and B actually this, and B is actually this. All right, so therefore the needed number is A plus B, which is as specified. Okay, and because this is proved by induction, this is assumed to be true. This is assumed to be true. Therefore, the sum of them are true. Okay, as we are, therefore the sum of them are true because this is true, this is true, and we argue that adding them together give you the answer for him. Therefore, it is true. Okay, so this is proved by induction, and I'm done with this. Are you okay? I want to show you one thing which is very similar to this is last week. Last week we talked about recitation number 4, Q4, question number 4. In the credit limit case, we all right, here is the answer. Let me just pull out the right. So the credit limit case, so this is a changing coin, the same thing, or maybe use here can do. All right. So if the total schedule unit is less than the maximum credit, then you have no issue. You just return the schedule. If the maximum credit is less than zero, then there's nothing you can do. You have to return empty set. Otherwise, schedule one is talking about taking the schedule without using the first cost. Then without using the first cost, this is with the first cost. So you see this analogous or the similarity with the coin change. This one is without the first cost. This one is for sure with the first cost. All right. And between the two, you want to find the one who is the longest. And that is the schedule you want to take. Okay, if schedule 1 is longer, you take schedule 1. If schedule 2 is no shorter than is longer, then you take schedule 2. So this is another solution to last week when we talk about the credit limit, taking the largest of the courses, the most number of courses with the maximum credit. And last week, I also show you my solution. My solution was that I do not use this recursion. And some of you use the sorting. Of course, you can sort and then you can then include smallest one by one, or you can drop the largest one by one. So there are two ways down there. Here, I don't use sorting. I go through a loop to find the largest, then I drop him. All right, and continue doing that with a while until I don't exceed the maximum credit uh, limit. Or I could have changed this to find the smallest and include it into my schedule. Okay, that will be another way. So there are altogether four ways. Whichever way you're talking about, actually, it doesn't run away from the fact that here is the argument. Right? So whatever way it is, you are making the premise that you want to include those among them, the smaller in credit units. Okay. So in the argument here, what I'm going to show you, which is also posted in the forum, is simply this, and you can digest that. This is proof by contradiction. So this is suppose you have a solution that doesn't have all the smallest credit unit. So a contradiction means that it contradicts whatever I want to ascertain. All right. Just now I said that I want to ascertain that for sure the solution that we have is one with all the smallest credit unit. So now by contradiction means that there is a solution that doesn't have all the smallest credit unit. And then from there you argue that you are having trouble because among them, the guy which you can assume without loss of generality, this is WLOG, without loss of generality, you can drop the guy at the end and add the guy that wasn't included, and you get the new schedule. And this schedule has the same number of courses, therefore you're not missing out you are still having the maximum. And at the same time, the total credit is no larger than what you already have, and therefore it still is a solutions. And by extremal property, this is another keyword, meaning that you keep doing this thing until you don't have any more of this, and therefore the contradiction is established, and therefore you have a proof. Okay, this may sound a little bit foreign to you if you are not familiar with mathematics, but this is the common things in mathematics. What you will want to ask, actually, let me quickly run through this, is that what is a proof? Actually, since young, you have been doing proof, all right, because you know how to do addition. 1 plus 2 plus 3 is 10. Why? It's not that you, of course, we are so familiar with this, but it's that you are doing step by step. 1 plus 2 is 3. And then the 3 plus 4, 3 plus 3 is 6. 6 plus 4 is 10. So that's how you do step by step. Proof it's always a step-by-step argument. And each step leads to another step is through some of the fact or some of the statement that we have previously proven. All right, so these are the logic that one must have when they are doing proving. So it is always a series of statements that concisely presenting the argument. So you see that just now this argument here, okay, this is a short description of something in disguise. All right, it's covering all the cases that could happen, but we have found a way to write it in a concise manner. It is the same as we have found a way to write a program in a concise manner. All right, so these are all very similar that you can be sure of it's working. And here is the same thing. A proof is always a series of statements, but it's presented concisely, and yet it covers all the cases. As such, we are able to present things to you. All right. Of course, there are proof in the world that take 100,000 pages kind of thing, but those will require the computer assistance. But here, usually, whenever proof that we encounter are proof that people usually know already, and there are always ways to write them in a very short manner or concise manner. Okay, one last thing I should tell you. People always have these mistakes. There are many ways, many proofs. So you have seen proof by contradiction, proof by induction, proof that I write statement by statement in the program. They are proof by existence and so on. But there's one thing that you have to be careful not to fall into the trap of proof by examples. Okay, you're giving me examples and then you say that, therefore it is true. For example, here in the program, it's the same thing here. In a program, you cannot tell me that you run enough examples. Example has never been enough, okay? To tell me the program is correct. To tell me program is correct, you have to have some logical way of proving it, or you have to prove me that all your examples are actually collectively, it's a complete set of what the program needed to handle, right? Or a representative of complete sets of what the program had to handle. Therefore, proof by example will then work. Otherwise, proof by example is a no-no for sure. Okay, one last statement, but an important one to you. Mathematics actually play an important part in computer science. Right, that's why you see all these kind of argument. They are all logic. Okay, I'm done. Any question? Yeah, okay. Give me a check and your TA should be here shortly. All right, let me just repeat this again. You do not need to really know the this kind of statement by statement or this kind of complete proof, but the minimally you must know how to tell me what you want to prove. All right, basically, these are the two statements. What are you trying to establish? Then, as I suggest in the forum, right, you should for your learning, you should look through those programs and then see how why certain thing is actually correct. All right. So this is actually pretty interesting because you must question yourself at this level of education. You have to question yourself why certain thing is true. Okay, and sometimes you can actually beat me that I'm wrong in making some assertion. Okay, let's see. Junjie is here. Hi.
Hi.
Okay, you I make you the host and you take over. Are you
Yep,
okay?
can. Yeah.
Okay, make host, change host. Okay, it's yours. I will take my leave now.
Okay,
Okay,
bye.
bye bye. Good night.
Okay, guys, I'll start at 8 p.m. Feel free to take a break. All right, hi everybody. So the time is 8 p.m. already. I'll start the tutorial now. So there was a question about proof questions. Uh, these kind of methods like proof by contradiction, induction, those kind of proving methods are actually more of like math course uh concepts. So this a CS course typically will not test these sort of math proving questions. If prof mentioned something about needing to know the statement by statement. Oh wait, prof mentioned that minimally you must know how to tell me what you want to prove. This kind of things is it's just like basically you need to understand whatever implementation you make. And at most he may ask like a short text question that may ask you to explain your implementation. But I've never seen this kind of proof questions in past year papers. I've done like a lot of the past 10 years of papers, and the past few years of CS1010X papers, the one set by Prof. Tan, I didn't really see sort of cool questions. So you don't need to worry about those. If you want to be more certain, you can ask Prof directly next review. But you can also check out the past year papers. If you don't know, they are in the work bin on cosmology. So find the work bin section and you can find all the past year papers for the midterms and finals and practical papers. So you don't have to do them all. You can just do some to get a feel of what kind of questions that Prof will test. So Prof said the past maybe 5, 6 years of papers, except for one of the recent years. I think the last year's paper was set by a different prof type. But you can just try the past 6 years of CS10X papers. All of them are set by prof type. So, okay, let's get started with tutorial 4. Tutorial 4 is on higher order functions. I need to make sure that you guys can see my screen. Can you guys hear me all right? Can I get a thumbs up? Okay, so let's just start. So for question 1, using composite Simpson rule. So composite Simpson's rule is just like a math rule that allows you to find the integral of a function, approximation of it. So now you need to transfer it to programming. So you need to write a Python function that does what composite Simpson's rule do. So the first part, it gives you all the information, all the formulas you need. And there are actually a few different ways to do it, so that you can write it iteratively or recursively. So can I see your solutions? All right, so let's go through the different ways you all came up with. All right, so for the iterative version, I took Zhen Yu Cheng's solution. Okay, Zhen Yu, can you explain how your solution works? Hi, Zhen Yu Cheng, are you there? All right, it's okay. I'll just go through your solution. Let me see. All right, so he takes the same H definition given in the question, calculates the result using the F given, and iterates through a loop from 1 to n. And he checks if k is odd, you add 4 times the F. Else, if it's even, add 2 times the F. And it looks like he manually adds the result. Yeah, he manually sets the result as 1 times the F function. And for the last part, he manually adds it with coefficient of 1 times the F function. Yeah, and then he returns it times H divided by 3. So this is another iterative way of doing it, I believe. Oh wait, no. Seems to be doing recursion. Okay, let's see. Who sent this? Jin Kai, can you explain your solution?
Okay. For my recursive solution, since we can see that except for the first and last terms, which are the coefficient is 1 inside, and then we can see that for starting from 1 onwards, y1, yeah, which is an odd number, the coefficient is 4, and then for y2, then the coefficient is 2, which is an even number. So use the modulo to filter between odd and even, except for the first and last term.
Yep. Right, thanks. So this is another way you can do the question using recursion. We actually didn't see a recursive solution during yesterday's tutorial, so it's nice to see a recursive solution here. There are also a different way of using a recursive solution using a call to sum. So can Min Jin Leong Ng explain your solution using sum?
Right. So what I basically did was I made use of the sum high order function to calculate all the terms from y0 to yn. So I input this function called exp, and exp basically calculates what coefficient to multiply to each term. So if it's like a y1, then you multiply to 4. Then if it's a even, then you multiply to 2. And then I return h3 multiplied by the sum of all the terms. H over 3 multiplied by the sum of all the terms.
Yeah, thanks. So this is a very cool way of solving the question using sum. So a common theme with some exam questions that could come out in the midterms or finals is that they may ask you to write your solution using a call to a lecture taught function. So like sum, accumulate, fold, fold to, those functions that you've learned in lecture. There might be some questions where first is a simple question where you implement your own solution. So let's say you implement your solution like this. Then they'll ask you to do the same thing, but with only a call to sum. So what you have to do is you write in the inputs, what you use as your term A, next, B, that sort of thing. And if you want to see some examples, you can look at the work bin for past year papers. So they can get quite tough. So maybe the base question was easy, part A was easy. where you wrote your calculate integral, it will be easy. But then the part B could be difficult because it forces you to do the same logic with a call to maybe fold or accumulate. So you have to think about what you have to pass in for your term, your A, your next, or B, and whether you want to use any helper functions before. So be sure to practice those questions. All right. So let's move on to question 2. So write a function gk that solves the following product. So it's very similar to the sum notation, but this is with product. So this calculates the product. So, all right, so let's see your solutions. You need to use the fold function. So this is an example of those questions that I was talking about that could come out in exams. Write gk using a call to fold. Let's see your solutions. All right, Zhiyan, Cai, can you explain your solution?
Okay. I first define the function fold, which when n equals to 0, it returns 0. Then else it'll return the operator with the function and fold with everything but n minus 1. Then I return then define the function g, which returns fold uh fold with the lambda xy, takes in inputs xy, and basically it, it does the right hand side of the g of k, which is basically x minus x plus 1 squared. That's the
Yep. Okay, so yeah. Yep, correct. So your solution basically does this function k given as math. So this is another way of doing it. So for this kind of question, when it comes out in exam, so usually you get like 4 boxes where you input what you write for like the operator, the f, the n, and there'll be another box for like any predefined functions that you want to define, maybe helper functions. So this is the alternate way. So this will go into the box for the helper functions, and you simply just call whatever you define as the input to op, to f, to k. Otherwise, you can leave the top box empty and just write in lambda functions for what you pass in as op, for what you pass in as f, and what you pass in as f. Yep, so there's basically only one way of doing it. Either you just put in the inputs, or you can use helper functions. So if you want to see examples for this, you can look at the work bin for past year papers. Yeah, and both these solutions will work. So let's move on to question 3. So show that sum is a special case of a more general notion called accumulate. And so these are some functions that you have been taught in lecture. So you write the accumulate function. So let's see your solutions. All right. So for part A is expecting a recursive approach. So there's basically only one way to go about this. So let's have Bruce, Samuel, Imalo explain your solution.
Hello.
Hi.
Okay, so accumulate takes in a combiner, base, term, A, next, and B. Combiner is how it combines the rest, how it combines with the next terms. So example for sum, it will be plus just now the pi function from the previous question. This will be a lambda function that will do a multiplication with its two inputs. Term will basically for each term, how it will transform. It's a lambda function to transform it into, let's say if you want to square this, let's say if you want to accumulate all the squared functions, then this will be the term. This function will be used to transform to do all the squaring. So so A and B will be your your start and ending, your starting number and ending number. So the next input will basically increment A or decrement accordingly until it's bigger than B, which will return the base input. So yeah, then just plug in accordingly into a recursive function.
Yeah, thanks. So yeah, so this is the simpler part of this question. So for this accumulate function, it's easier to write a recursive solution. I suspect most of you will have trouble with the iterative approach. So first, let's make sure that everybody understands how the accumulate function works. So yeah, as Bruce mentioned, so we basically go from indexes A to B, and the next function, which is one of the inputs, will basically decide how we go from index to index. So let's say A is 1 and B is 10. And the next function is just a simple increment by 1 function. So we'll go from indexes, we'll consider the indexes 1, 2, 3, 4 until 10, until B. And if next was, let's say, a different function that adds 2, then we'll actually jump from 1 to 3 to 5 to 7 up to whether we hit the base case or the last index. Yeah. So term is how we derive the actual term. So if the term is, let's say, a square function, you'll take the index and apply the square to get the actual term that will combine. Combiner can be anything, any math operation that takes 2 inputs, and it can like times, it can add, it can minus, it can divide, it can do anything related to 2 inputs in a lambda function. Yeah, and base is just your base case, whatever it starts out as. So but before we move on, let's see how we can define sum as a simple call to accumulate. So let's see your answers. Right, yeah. So there's basically only 2 ways to go about this. So this is the structure of what it may look like in exam for your paper exams. So for the midterms, what you'll likely see for this question will maybe be 6 boxes. 1 box to put helper functions if needed, and 5 boxes for each of the inputs. So for each of the inputs, you will need to write in what you pass in for your combiner, base, term, A, next, and B. And this box for the helper functions is optional. Depending on whether you implemented anything, that will be passed into the inputs over here. So one way to go about this is using lambda functions. That way you don't have to write any helper function, you just pass in the lambda functions itself. So your combiner is a simple addition, because sum always does addition. Your base is 0, because sum's base case. Where is sum? Sum's base case is return 0. So you literally look at how similar accumulate and sum are. The only difference is whatever they return in the base is already set to 0. So simply just put your base at 0. Term is the same thing. Use the term in your sum function, and you can pass in the same A, next, and B inputs for your accumulate. So as you can see, sum is a more specialized version of accumulate. It basically, the only thing that's different is it forces the combiner to be addition, and it forces the base to be 0. Just ignore this. Okay, now give an iterative solution, accumulate iter. So I suspect most of you will have gotten this wrong the first time you try it, but hopefully you guys understood and will manage to solve this in your tutorial. So can I see your solutions for accumulate iter? All right, before we go through your answers, let's look at a common wrong answer. So the thing about the recursive solution is, let's see. The thing about the recursive solution is it has a specific order where it will add everything together and collapse everything together. So if you see this representation on how the math adds together, you'll see that look at from how combiner combines the terms from the first call to accumulate. So let's say you had this call to accumulate. First, you combine the first term, which is over here, with the next call to accumulate. So this is the entire next call to accumulate. And in the second call to accumulate, you generate your second term and combine it with the third call to accumulate, and so on. So in that call to accumulate, you have your third term, fourth term, which is here, and the last recursive call to accumulate, and then you reach your base case where you add the last one, yes, last 6 together with your fifth term. And this is how you add together. If this was addition, this would matter more for like non-commutative operators, like when your combiner is using non-commutative operators like subtraction and division. So those two operators care about the order in which you combine your terms. So like especially how the brackets work. So remember how this looks for recursion, and let's see the incorrect iterative solution. I have to rename it. As you can see, it collapses the terms together in the wrong order. You see, it adds up like this. It puts it in the wrong order. So it doesn't correctly mimic the same logic and the same process as the recursive function. So there are things you need to do to change up how your function works within the loops. And there are many ways to go about it. So let's look at one way. So this is, which solution is this? Let's see. Okay, Chen-He, can you explain your solution? Okay, I'm gonna assume that your mic doesn't work. Let's go through your solution. Okay, so what he did was initialize a empty tuple to store his terms, and he iterates through it as normal. But what he does is when he calculates the terms, he actually adds it to the front of the tuple while incrementing his index. And he initializes his result as the null value, and he combines it. But notice that the terms were already in reverse order. So this is essentially adding each term to the front of the tuple, makes the whole tuple basically reversed at the end. So you will have to do something like this in your approach. So let's look at a different way of doing it. Callum, can you explain your solution?
Hello?
Hello?
Okay, first I generated the sequence of terms. So the terms will store the values. FA1, FA, like function of A1, function of A2, FA3, FA4 until FAN. And then after that, I did the while current less than or equal to B. So I iterated through the range using the next function. So yeah, so after that, FAN, the recursive definition, not recursive, the iterative definition ends with FAN base. So I initialize the result equals null value. And then after that, I did the 40 in reverse terms, because I wanted to process the list in a reverse order. And then, that's it.
Yep. So this is
yeah.
another way of going about it. So you generate all your terms first, and then you reverse the whole thing and iterate through that. So the reverse function basically takes any iterator, so a tuple, a list, or anything, and returns a reverse object. So technically it doesn't return a tuple, it returns a reverse object, which is another iterable that you can iterate through using a for loop. So since you go through it in reverse order, you will mimic the same logical process that a recursive function does. And as you can see, the way where you collect all your terms together will be the same as the recursive way. All right. So I'll actually show some slides on the tracing. Let me go get them. All right. So you could trace through this in Python tutor if you want, but I already made some slides going through this. So this is how you would trace it on paper. So for, let's say, this call to accumulate, I set my combiner to a subtraction lambda. So this takes in two terms and it returns subtraction. So it uses a non-commutative operator to demonstrate how this will work. For my term, I just use the identity function, just a simple lambda that returns the index itself without changing it. And for the next input, I just use an increment of 1. Yeah, so this is our example call to accumulate. So I actually use these shorthands so that it's easier to read. So it's easier to visualize the different steps. So we go through it one step at a time, like tracing through how Python will evaluate this. So first, so you can see, because A is not more than B, it will return combiner of term of the first index and the next accumulate call. So term 1 evaluates to 1, right? So you get combiner 1 and your next accumulate call. So this is your first one, minus, because of your combiner. Combiner will cause this minus, and this is your next call to accumulate. And note how the brackets work here. So 1 minus this whole thing, this entire call to accumulate. So the second call to accumulate will get 2, your second term, plus the next call to accumulate, and so on. This call will accumulate, will go down here and get 3, minus this call to accumulate. And that call will cause 4, minus the second last call to accumulate, and go down to here. Your last term, minus your last call to accumulate, which is your base case. So notice now A is more than B. So this will get evaluated as 0, because this is what you put in for your base or your null value. And notice how this evaluates. This is how the terms are collected. So this will matter for non-commutative operators in your combiner function. Yeah. Okay, let's move on to question 4. Question 4 here is a ADT question. So your task to implement a point ADT structure using any way you want. So let's see the different approaches you all came up with. So what the question is expecting is you need to represent a point as a pair of numbers, an x coordinate and a y coordinate. You need to prepare a constructor, make point. You need to prepare two getters or selectors as they are known. X point that returns the information from that particular point. All right, so there's many different ways you can implement your point using any data structure as long as it is able to store the information about the x coordinate and the y coordinate and provide getters to retrieve those information. So these are two simple ways. You can either use a tuple to represent your points and simply for your getters just index them. Same thing for lists. It's the same way. Just know the difference between tuples and lists. If in the future your implementation needs to have setters that change the x or y coordinates of your point, it will be different for tuples because your setters will have to return a new point because as you know, points tuples are immutable and you won't be able to edit the point if you implement it as a tuple. Whereas for lists, you can simply just change the element at a particular index to mutate your list, the underlying list representing your point. So recognize the differences. So here we have a little more of a unique way of doing this. So let's have Chin-Kai explain how your implementation works. Hi, Chin-Kai.
Hi. So I I I so basically since we index starting from 0, so if we want to get the first point, we can get to x point by by implementing p0 and then but yeah.
Okay, I think I can explain it in a bit more depth. So maybe you don't really understand how this works, but okay. So your make point returns a lambda function. So how you implemented your constructor is like through a HOF, a higher order function. So higher order function is a function that either takes in other functions as its input or outputs a function as its input. So for this case, it outputs a function. So your point representation is basically a function. So you can think of your point as a function. So what your constructor did was to take in two inputs already, take in two inputs representing x and y. So whatever these x and y inputs is remembered by the function that is going to be returned by your constructor. So your constructor returns a specific function, a lambda function, that takes in a p value later. So if the p that will be input to this function is 0, then you return x, the original x that was input to the constructor. Else it will return y. So let's say p1 equals to make point 2 and 3. p1 is implemented as a function. So as you know, functions can be called, right? If you were to call p0, you get 2, which was the original x that was input to the constructor. And if you call your point with 1, you get 3, which was the original y that was input to the constructor. So yeah, so if you were to, let's say, call type on p1, I don't know if it's a function. So there are different ways you can use functions to represent your point. So I have one solution by Bruce. So this is another way of implementing your data structure using functions. Bruce, can you explain how yours is different?
Okay, my implementation is similar, but instead of using numbers to check, I use a Boolean input x point to check. So if x point is true, it will return the x coordinate. If its x point is false, it will instead return the y coordinate.
Yep, thank you. So yeah, this works very similarly to the above part, where instead of checking for 0 and 1 for the input calls, you're checking for true and false. So yeah, so using functions to represent your data structure is a little more complicated than using something more intuitive like tuples or lists. So you don't have to do it, but you should be able to understand it if this was presented to you. So let's say this were to come out in an exam and we had a predefined ADT already, and it has constructors and getters making use of functions making use of higher order functions in your implementation, you need to be able to understand how and why this works. And the question may ask you to build upon it, write more getters, or like write constructors for a different point. You need to understand how to work upon it. So let's say the question only gave you the constructor and asked you to implement the getter. So you need to understand how to implement the getter. So you need to read the constructor, understand that it returns another function. So for your getters, you will need to call that input. Yep, so we move on to question 4a. So now we are creating an ADT representing a segment, a line segment that has two endpoints. So this segment needs to store information about its starting and ending point. So those points are the same as those that you implemented here. So this is your point ADT, this is your segment ADT. So let's see how you implemented your segment ADT. So how you do this part may be different depending on how you implemented your points. All right. Well, this question is very similar as the point. So it's so similar that segment also takes in two inputs. So instead of keeping track of its x and y coordinates, it actually keeps track of its starting point and ending point. So what you could do is be more descriptive in your name here by naming it start point and end point instead of just P1 and P2, because we need to understand like what does P1 and P2 actually mean, because for your segment it actually has a specific meaning. Point 1 is the start and point 2 is the end. So if you were to implement it with a tuple, your getters will simply index it using 0 and 1 depending on what order you put them in. Same thing as if you implement it using a list, you index them directly. And the same thing goes for the difference between tuples and lists. So if you had to implement setters in the future that change the data within, it will work differently for tuples and lists because tuples are immutable, while lists are mutable. So same thing is exactly the same as the previous question for if we use functions. So what Bruce did was he implemented the segment as a lambda function. So his constructor will take in the two inputs about the start and ending points and return a lambda function that expects inputs either true or false, so that it will return either the starting point or the ending point. All right, so let's move on to question part 3. So using the selectors and constructors that you implemented for your point and segment ADTs, implement a midpoint segment function that takes in a line segment and returns its midpoint. So let's see your answers for this question. Midpoint segment. All right, okay, so there's not many ways of doing this question. So let's have Godwin explain your solution.
Yeah, so I start off by finding the starting point and the ending point of the segment. Then I find the x coordinate of the midpoint, which is essentially just retrieving uh the x coordinate of the starting point, summing up with the x coordinate of the endpoint, then dividing this sum by 2. Then I repeat that for the finding of the y coordinate, and I just make a point using the x coordinate and y coordinate of the midpoint.
Yep, thanks. So one important thing that I need to bring up in all ADT questions in our exams is we are looking for whether you're breaking abstraction. So go on you for using the constructors and getters that you implemented in your previous part of the question to work with points and segments. So to get the start point and the end point, you actually use the start segment and end segment to retrieve the information from the input, from the segment input. Yeah. And for your middle point, you use your getters to look into your start and end points to retrieve the information. And finally, when you return the point representing the midpoint, you use the constructor to construct a new point using the parameters that you calculated. So another way that could work is, let's say, you do this and you index it directly. But as you may know, this will be breaking abstraction. So like for midpoint, I just use a tuple. Yeah. So this will be counted as breaking abstraction because you know exactly how the underlying data structure behind your segments work. You know that it is something you can index. You know that it's a tuple. You can get the points using simple indexing. But that defeats the point of using an ADT. So the point of an ADT is that the user doesn't need to understand how it was implemented. It only needs to understand what inputs each function needs and what outputs the function will provide. So if you were to simply return a tuple, all this is understood as this is a tuple of 2 numbers. It's not actually a point because you did not use the point constructor to create a point. So this way only works because you know that a segment is a tuple. So what if you don't know that the segment is implemented using a tuple? What if it was implemented using the functional way? Then this will fall flat and it will not work. So you need to use the constructors and getters you implemented before and return a solution like this. So if you do break abstraction in an exam, you may be penalized. Especially for some of the missions, you do get penalized, like mission 6, the rogue train hypothesis. Be sure that you use the constructors, getters, and setters that you've implemented in previous parts or the question has given you, else you'll get points deducted from you because that is bad coding practice. Yeah. So finally, we have implement a representation for rectangle in a 2D plane. So there's many different ways of doing this. So let's see how you guys came up with for your representations. So this question expects 2 different representations, but there are like many ways you could go about this using different inputs and different getters. Any more solutions? Which when you look at quite a few, there are quite a few different ways of doing this question. All right, let's have Bruce explain your implementation.
So first, in my constructor correct, I create an abstract data type that uses a tuple with which is first element containing the length and the second element containing the breadth of the rectangle. Then I define my getter functions getLength and getBreadth, which were indexed into the rect directly to get the values.
I run, bro. I'm
And then for area, I use my getters to get the length and breadth, then length times breadth. Then perimeter, I use my getters once again to get the length and breadth, and I do length plus breadth and then times 2.
Yep, thanks. So this is one of the simplest ways that you can represent your rectangle. It only stores information about the length and breadth of the rectangle and doesn't store any information about the location of the rectangle, which is not needed for this question, but it's something that you must think about for different questions depending on their requirements. So for this question, they only requires you to be able to derive information regarding the area and perimeter of the rectangle. So really all you need is to keep information about the length and breadth. So let's see, there are no other ways that people have shown here. So I'll just show you some slides of a different way. So here is another way where you store actually points. So these are your point representations. You only store like the top right, top left, and bottom left, because that's all you really need to get the last point. So you don't actually have to take in the last point, because you can derive it using the first 3 points. So you can implement some different functions to get a line segment. So making use of your segment ADT and point ADT. And you can define functions to get the length of a segment to be able to calculate its perimeter and area. So yesterday we actually saw a lot of different ways, like taking all 4 points or taking only 2 points, the top left and bottom right. And from those 2 points, you can actually derive all the points of the rectangle. And from only 2 points, you can derive the length and breadth of the rectangle and return the area and perimeter. So yeah, I don't have anything else for you. So the tutorial is finished. So yeah, 9 p.m. If anybody else has any questions, you feel free to stay back and ask. You guys are dismissed. Thank you. Bye, guys. What are the pros and cons of using lists, tuples, and function and data type? And is T in an exam, they may force us to use one to solve. Okay, so for pros and cons of using lists and tuples, as you will know, like for lists, the pros is you can directly mutate the underlying data structure to change the data. So if the question tasks you to implement setters, which are like functions that will change information about a particular ADT. So if a point needs to be able to change its y coordinate, let's say it needs to be able to move. So using a list will be an easy way to mutate a point. Otherwise, if you use tuples, you will need to return a new point because there is no way to edit the information about the old point. And in an exam, they may force you to use a particular way. So it's good to understand all the different ways to implement it. And obviously in an exam, they may already just give you one of the ADTs. So let's say it was a ADT with like points and segments. Maybe they'll implement a point first and task you to implement a segment using points. So the point will be predefined already and you must use the constructor. Or they may ask you to implement the getters given the defined constructor already. So you need to see how the ADT was implemented and decide how you implement the getter. So if it is underlying tuple representing the point, you will need to index it in your getters. If it's a function, you need to call it. So other than mutable or not mutable, what else though? It depends on the ADT. So let's say we have a shopping list ADT and like products. So products will need to keep track of its of the name of the product and price, right? And the shopping list will be, or the shopping cart. Let's have a cart. So the cart will need to keep track of the products inside the cart. So it will make more sense for the cart to be a list. So you can like keep all the products inside it. And there's not really much other differences. So you just need to understand like what can a tuple do, what can it not do, what can a list do. Other than the immutability, they are quite similar already. One particular difference between tuples and lists, of course, if the thing about adding something to a tuple, right? It forces you to return a new tuple. So tuple concatenation will be ON, right? But list appending will be O1. If they don't say anything about it, then no. If there's a need for the code to be efficient, then they'll probably say it. There was a question in past few years, I think 2 years ago, set by a different prof, where the last question was like a 30-mark question where if you implement a ON squared, no, an ON solution, you get the full 30 marks. If you implement an ON, if you implement an ON solution, you get a full 30 marks. If you implement an ON squared, you get 10 marks deducted. And if you implement the trivial solution, the naive solution, which is an ON cube, then you only get 10 out of 30 marks. So you can go look for it in the past year exams. It was set by a different prof done. But that was in the practical exam. It was explicitly stated in the question, like the amount of marks you get for different time complexities. And it's also possible, very common for the question to ask you the time complexity of your implementation. So it doesn't really care about whether it's the most efficient, but it will care about whether you actually answered correctly and understood the time complexity of your solution. So like you can go look through the past year papers. There are questions where they ask you to implement a function to solve a particular problem and then explain the time complexity of that implementation. All right, if there are no further questions, I'm gonna end soon in 1 minute.